All right. Hi, welcome to the class. Let me share my screen. We quickly look at the syllabus and then get started with the slides. So here is our the basic version of the course. This is the advanced course. So we covered these topics, especially the PCA last time. MDS was left out. And then we wanted to cover this topics as well. Anova, confidence intervals, Nonparametric Tests. So let's do the Anova and confidence intervals in this test first in a little for some time, and then we move to MDS. And then we can. I will give you an overall landscape of different areas in data science before we close the class. It would be like some sort of like a cloud or like a block diagram that will give you what are the different things you can cover, what are the different areas that you can continue your learning on, or you can focus on some area that interests you afterwards, that kind of thing. Okay, so let's get started with Anova. Okay, so Anova actually stands for analysis of variance. The situation where you use it as follows. So if usually the t-test, z-test, the hypothesis tests are basically to compare two arrays, right? Two vectors or two columns of data from two different variables or two different groups. But if you have more than two columns that you want to compare and make some decision if they're significantly same or different and stuff like that. Or if you have a group of 5 columns, another group of 5 columns, how do you compare? You know, all these kinds of, or we have a set of columns, but some columns fall under some common category, another set of columns another category, basically. How do you compare? So basically you have your null hypothesis in a standard ANOVA is whether all columns are similar behavior or not. Your alternate hypothesis is if they are not the same, right? So you want to detect that. So hypothesis testing is what we covered, right? So ANOVA is again a special case of that. So hypothesis testing, just for a quick review, you basically had a null hypothesis, which is this one. You have an alternate hypothesis. You want to go with one or the other based on statistically what you think is significant. All right. So the idea of ANOVA is literally based on looking at so you have different columns, right? Different groups. So the idea is you want to see how much the variability is across the columns versus how much the variability is within the column. So by variability, literally I'm meaning the variance. So variance is basically defined as the deviation from the average, right? So if variance is large, you know, it is very variable. You know, so its spread is more in the data. Otherwise it is close by. So what we do is we look at the variances across the groups, which is known as the variance between groups, or this is also known as between treatments. The groups are called treatments. And this is within individual groups. So you want to see if this is a very large quantity, then it means the groups are very different across each other. So people can ask, why not just look at the numerator? Isn't it good enough to say one group is different from another? Not necessarily, because you might have a lot of variability within the group as well. So you don't know if this is being contributed by these numbers or these numbers. So you want to separate this. So this is like more like noise. This is like the signal part. Usually in hypothesis testing, you have this signal to noise kind of a ratio in general for most hypothesis tests. And the beauty is for hypothesis testing, if this was your test statistic in general, this is the behavior of your test statistic. You also need to know what distribution it satisfied. But the beauty is the ratio of variances of random variables is always going to be a very special distribution known as F distribution. So you know the distribution beforehand. Yeah. So this is exactly what he's saying. Let me remove this part. Open it again. Oops. Okay. So, so yeah, so you're comparing whether the variance, the null hypothesis, if nothing is, if everything is same, it means the variance is between the groups across the columns or across the variables is same as is similar to the variance within the columns. But otherwise it is not, right? And you want to see how much different it is. So this is literally example representation of your data set. You know what? I need to get in the charger for a second. I don't want the battery to stop. All right. So you have this data set. Say you have 4 columns of data. So these are what are representing as 4 treatments. And then obviously you have many observations in your data set. Here, since it is like an example, you have like about 10. You have 10 observations per group. So now the idea is you want to figure out statistically through Anova whether these groups are significantly different behavior or similar behavior from a statistic standpoint. So basically when I say within group variance, I'm looking at how these numbers are varying within the group itself, or how these numbers are varying within this treatment 2 itself, how treatment 3, so and so. When I say between group variance, it is how these numbers are varying across these numbers. You know, are they similar, or are they varying a lot? That is the idea. So for example, this could be for example, you gave 4 different medicines to some particular condition, a group of people with one particular condition. We divided them into 4 groups. You want to see if all 4 medicines that are in the market for that condition is giving you the same effect, or are they giving different effect, right? That is the situation here. So obviously you can compute the means. Because you want to compute variances of any kind, you need to compute mean first, because variance is what? It's the deviation from the average, right? So these are individual group means. And then you can have within group variances. So this is the variance within this group. This is the variance within this group. So you're looking at the deviation from the mean and then dividing by total entries by -1. So on. So you have 4 variances, you have 4 means. As simple as that. These things even Excel can do for you, right? If you write a quick formula. All right. Now you're looking at, the idea was to look at within group variance and also then look at between group variance. So this is the within group variance, which is what these numbers are, 4 numbers. So you can sum them up. So you can sum off. So this is known as the sum of squares of within. So basically you're adding these variances up, which will end up being the same as this value. And then now we want to look at sum of within is the within group variance here. So this was done. Now we want to go at between group variance. So now what you do is, instead of computing individual means, you compute the overall mean of your entire table. So all 10 values times 4 columns. You compute the entire mean, and then you look at every individual entry and you see how the variance is there, one group at a time. So you're looking at that variance. So this is the sum of squares between variability of the group means compared to the grand mean, variability due to it. Okay. Then there is something called total sum of squares. This is basically the sum of these 2 variances. So this is the one type of variance is one type. If you combine this, you'll get the overall variance. Okay. So so that is what we are doing here. So if you see here, in terms of the sigmas, here there is double sigma, double for loop, right? So because here you are looking within, which means there are 4 groups to look at, and within each group there are 10 values. So that's why you have this double for loop, double sigma going on. Now between, you're only looking differences between the 4 group means, 4 group variances. So you're only looking 4 groups. Then you have total sum of square. Okay, so this is just like a table, the same numbers we're putting it here and here. This is the ratio of those sum of square between by sum of square within. So this is known as the ratio of variance is always going to have a distribution called F distribution. So now once you have a distribution, you can have a test, you can do your hypothesis test and decide, right? Because let me do a quick review of that hypothesis test part, the structure of hypothesis test. We've discussed this in week 9, but there are only 3 things you need in a hypothesis test. One is you want to specify what your null hypothesis is in any hypothesis test. So you specify something. Then you want to specify what is the alternate, because you want to go with either one, or say this is true or this is, and you reject this, or this is true and you reject this, right? That's the only option. That is first step. And then you have what is known as a test statistic, TS, which is something you compute from the data. The test statistic, you will also have to know the distribution of the test statistic. So is it normal distribution? Is it F distribution? Is it T distribution? Is it chi-square distribution? So on and so. There are so many distributions, right? There are many kinds of normal distributions well known. F is what you saw in Anova. T is what you'll see in t-test, so on and so forth. There are many distributions also. So all you need is define your question of what the two hypotheses are. You have to know what t-statistic is required to decide on that particular hypothesis question. So it could be hypothesis based on means, it could be based on variances like in Anova, so on and so. So the test statistic, you should also know what the distribution is. And then the idea is follows. In order to make the final decision of whether you go with H0 or whether you go and reject H1, or whether you go with H1 and whether you reject H0. These are only two options. You go with this option or this option is decided as follows. I said t-statistic has a distribution. So say one particular question t-statistic had, the test statistic had say a normal distribution, for example. Then your normal, for example, some normal of this kind. There are different kinds of normals, right? So then what you want to do is, based on that, and also this test statistic will follow this distribution only under the condition if H0 was true. So it is not, it is a conditional distribution. So it is the distribution, so only given that H0 is true. Only then you have either normal, this, that is the structure of the hypothesis. That kind of a distribution you want. If it were true, how will the test statistic behave? So this is the thing, this is like, for example, if the coin was, H0 was simple as like a cartoon example, coin was fair coin, heads and tails fair, you don't know, equal possibility. And say alternate was, say coin was unfair coin. One particular coin, not the general coin you get in market, right? So if H0 was true, what is the test? One ideal test statistic is, like the number of, if you do n, the number of heads and tails you'll see will be equal probable, right? So that is a distribution. It will be uniform distribution. So that could be, but if H1 were true, and you will see your behavior and you will see, oh, it is not looking like the test statistic as it is supposed to be when H0 is true, then you will say, oh, something is wrong, then maybe the H1 is true. That is the idea here. That's why you go with one condition. Under that condition, what is the test statistics distribution you want to know? So that when you test for really whether you go with this option or this option, you can see how much you're deviating from this distribution assumption. So if you're deviating, then it means it's not possible that your H0 is true. Then the question is how much deviation is, what is the threshold of that deviation, right? So that is why you're looking at the test statistic. This is the behavioral test statistic. So this is showing, for example, if it was normal, in one particular case, if this was the behavior, what is distribution? The values are on the x-axis, y-axis is the probability, right? So this is the value of the test statistics, and this is the probability of the test statistic, right? P of TS. This is TS. So as you see, some values, maybe these values, anything between this and this value of test statistic are more probable because you have higher probability. But if you observe a test statistic somewhere of like this value of this value, then it is very impossible or very low probability that the test statistic will take this value if the H0 were true. So you will say, oh, this is a rejection region. So I will say, no, H0 is not true, H1 is true. If your test statistic that you're computing your value falls somewhere here, then you compare with respect to this distribution, you say, oh, it is falling in a high probability area, so H0 is true. Okay, that is a structure. So same thing we are doing here. What is changing in Anova? Only a few things. H0, H1, you're obviously defining whether your treatments within the groups, across groups are same or not the same. Your test statistic is based on variances now, because you want to see between variance is very much different from within variance. So that is a statistic. And now we know, since it is a ratio of variances, we know in Anova case, we are going with F distribution. So F distribution has a specific shape. When you are going with F distribution under the assumption if H0 were true. Then you look at your test statistic and you compare with this curve of F distribution, and you will see if it is falling in acceptance region or rejection region. Acceptance region, you go with null hypothesis. Rejection region, you go with alternate hypothesis. Just to show shape of F distribution, I want to open Wiki. Wiki always says, there you go, here you see. So this is the F distributions. So it's not looking like normal. Depending on your choice of parameters of mean and variances, you will get different F distributions. Okay, so going back to the, oops, where was the slide? Slide was here. So you define null and alternate for ANOVA. We know our ratio. This is our test statistic, and we know it follows this distribution. So you know the shape of this curve. You can compute this from your data. Then you see in this shape of the curve, is it falling in high probability region or low probability region? If it is in high probability region, then H0 is true. Low probability region, H1 is true. So we already told you how you compute the variances. It's just all just arithmetic. Like if you have a calculator, you can hit it, or if you have a computer Excel. But this computer does it quickly for you. All you give is the 4 columns of data. It'll do ANOVA. You call the function. It'll do everything for you. So you have the test statistic. You know the distribution. Now go to chart means. Look at the distributions. Chart means the chart is like just the plot of your distribution, but in a chart of numbers, so discrete values. So you can either look in chart and say, okay, is it in low probability region or high probability region? So now in the 4th thing, instead of cartoon numbers, you put real numbers here. So he computed the means for individual groups, grand mean, between square variance, then within square group variance. Then he populated all these numbers. Then he knew the F statistics. So yeah, this is a good version. He computed everything, and then he figured out whether they are the same or whether they are not based on the p-value. So for example, here he did 1, 2, 3, 4 ANOVAs. One ANOVA was based on whether calcium in school students' lunch. So apparently some school is offering lunch, their own lunch. So they are measuring some nutritious value. Like, are they offering junk food or like some like fried food or like something more healthier for the kids, right? So they measured maybe 4 different nutrients in the experiment. They went to many different schools. That is what their data was. So if you see, oh, I hate this part. Yeah, if you see something like this, you can imagine for one particular nutrition, you went to these many schools. And then you are seeing within students, and then within the lunches, across lunches, like that kind of thing. So, oh my God. Okay, we want to see calcium within school variation. You want to account for, then across school variation, across the lunches, because lunch is varying every day. You're not main, right? So, and similarly, you want to see if it is significantly different. It said here it means you reject it, which means they are different. Apparently, some schools are better. Here, you're not able to reject for iron. More similar behavior across schools. Folate, some nutrient you're able to reject. You're saying it is difference is there across schools. Zinc, it depends. If your p-value is 0.05, then it is not different. If it is 0.06, then it is different. So it's reasonably different. What does 0.05 p-value mean? It means about 95% guarantee probability you're having. That the conditional distribution would say it is null, that the null is true. H0 is true. So yeah, so he gave this example basically of what I said. Okay, so yeah, we're going into regression, which we don't need, which we did already. Any questions or anything? That is the overall idea of ANOVA. Whenever you say ANOVA table, you are checking whether you're applying when you have different groups. You are seeing if the groups are having variability or not. Groups are different behavior or not. So how do you do that? The intuition is looking at within group how the variability is, across group how the variability is, and see how the ratio is. If the across group variability is more than the within group variability, then there is a significant difference across groups. But this you are posing as a hypothesis testing problem, where I already told you what is the structure of hypothesis test, like before and here as well. So based on that, you get p-value. Okay, so now we go to another topic, so which is confidence intervals, and this is something we touch minorly, slightly, and then we go to MDS. So let's go to confidence intervals. Confidence intervals is, it's kind of goes along together with the idea of hypothesis testing. So hypothesis testing confidence, in some ways you can call it two sides of the same coin. Okay, so let me zoom this a little bit. Okay, I'll be using these two slides actually. So yeah, let's go through it. Again, I'll give you an overall overview and then we can go into specifics, just like we did for Anova. Okay, so yeah, let me tell you what a confidence interval is. Okay, say if I tell you to estimate the mean of some data, and say the data was say normal distribution to make things simple, and then you say, oh, this is the mean, then you will say, I will also give you an estimate of the mean with some confidence before and after. So I will say it will fall within some interval with confidence 95%. It will fall within an interval with 99%. It will fall within an interval with confidence 5%, which means you are not confident at all. That is the overall idea. Okay. So don't we bog too much about the math here. We'll go through it. But so an example confidence interval is like this. If you're going based on Z distribution, the confidence interval for the mean is this. So you will compute the average and minus this value, you get one number. Upper limit of the interval is this, and you will say with probability 1 minus alpha, with confidence 1 minus alpha. Alpha is 0.01 means you have 90% probability, so and so. But based on your alpha, this calculation is also changing, as you see. You will get an interval and then you will say, oh, the mean estimate of my mean will fall within this interval that I'm computing, those two numbers, with 1 minus alpha probability. That's the overall idea. Here it is based on T distribution. This is known as chi-square distribution. Different confidence intervals useful in different situations. Okay, that is the overall idea.
So what is alpha?
Sorry, what is alpha? Na?
Yeah.
Alpha, yeah, alpha is known as your level of significance you want. So sometimes some measurements you want very high precision, then you will say if I want high probability that it will always fall within the interval you're giving me, then you have to choose small alpha. Because if you choose small alpha like 0.01, 1 minus alpha will be 0.90, which means 90%. Right. If you choose 0.1, sorry. If you choose 0.05, then you will get even more probability, 95%. So alpha is just your initial choice of how much confidence you're looking for based on 1 minus alpha. That is the idea here. So I will move to now this slide. I just wanted to show that these examples here, this is a little more advanced slide because it's not advanced, but it is like suddenly you're coming in the middle of one particular lecture before some lectures have happened. 4 lectures have happened, right? This is 1805. So now this one is also in the middle, but is a little more well suited. But that showed you what I wanted to show you in the overall, the end result. Now I will go how we get to that end result. So, okay, yeah. So if you see, previous lecture was not about confidence interval. So this is the first time he's starting with confidence interval. Okay. All right. So there is an idea of what is known as sampling distribution, which means mean is a test, is a statistic you're computing, right? So is the ratio P in some proportion of successes, for example. So many different things you can compute. But even that mean is also has some variability. So mean itself has its own distribution that is known as sampling distribution. So what I'm saying is, I'm saying some maybe a height of students in class, right, is following say normal distribution is what I'm saying, which means my random variable is heights of student in some class or some high school or some middle school, whatever. This is the probability of that height. The distribution is that, right? It's a function that gives you probability. It's not a distribution function. Say it was following normal distribution in some situation. Now the distribution will have some mean, right? Which is this. This is the mean value. This is the variance, how much the variability is this distance from the mean. But this is in theory, this is known as population distribution. This is all population distribution. Like, yeah, if you had millions, trillions of data, this is what will happen, what he's saying with this mu, because you can have normal distributions for many different means and different variance. If I said normal distribution with mean and variance here, you will get some curve like this here. I said low variance, it will be very close by. If I say same mean but high variance, it will be very spread apart. There are many kinds of things. But anyway, once you fix the statistic, the mean and variance, you get one specific normal distribution. This is the population version. That is what I want to point to. Which means in theory, that is the truth. That is the reality, the God's truth kind of thing. But then you only have data. You don't have like trillion students in your school. You have 50 students in your class. Maybe entire school 500 students, 1000 students, whatever. But depending on how crowded or how big the school is. So then all you have is, if you did not know this truth, the true mean, all you can do is you can just estimate the mean from your data. So now is the sampling distribution. From your data, you are estimating the mean, which is a test statistic. An estimate of this. This may be, if it is a good estimate, it will be very close to the true estimate, which you don't know. But if it was the God's truth, if it is like a bad estimate, or if your data was very skewed, whatever, then it will be somewhere away. It will be here. So you'll be thinking it is a normal here, but in reality, it is a normal here. Right? That kind of thing. So since your data, your estimate comes from some normal distribution, even you know the true mean variance or not, you at least know that it is coming from normal distribution. You don't know what is the mean and what is the variance. Okay. You can estimate mean from the data, you can estimate variance from the data. And based on that, all you can do is say, I think it is normal of this mean and this variance. Right? But as you see, since the data is a random variable as a sample of your distribution, so the thing is, anything you compute from the sample is also a random variable, because this is, you're computing as a function of your data set, right? You're adding up your numbers in your data set, dividing by total, you get average. Then you're looking at deviations from that average, you're getting variance. But it is a function of your data. And if your data is a random variable, your function of random variable is also random variable, which means mu and sigma are also a random variable. What does it mean? It means mu also has some distribution with some mean and variance. Sigma hat also has some distribution, which is fair enough, because what you're seeing is not like one estimate of anything. Everything you're dealing with in statistics is random variables, right? So there is some distribution around this mean. It may be a mean, there is a distribution around the of the sigma as well. So that is what he's pointing to. So an average has a mean, so and so the variances of that distribution is this. So because your average also has some variability, right? It's not always the same average. So that is this variability. So and so for different statistics is giving different things. So sampling distribution allows us to make statements about the unobserved true population parameter. Unobserved, that means this one. You know it is normal, but you don't know what mean the true normal is. The true population parameter. That is what he meant. That says it population. In relation to the observed sample statistic, means from your data sample you computed statistic. So there is a distribution of this that is known as the sampling distribution. Okay, now this is useful in both. See, confidence intervals, hypothesis testing, I said two sides of the same coin in some ways. That's why both we mentioned in the agenda together. And then what else? Yeah, then there is a very popular theorem, very celebrated theorem. It's known as central limit theorem in statistics. Most of these intervals are based on that central limit theorem in general. Even your hypothesis testing, when we said the ratio of variances is chi-square, you know, in some form or other you can derive that is F distribution we said in Anova. Central limit theorem, for example. So it is all those derivations of distributions whenever you get normal, especially is through central limit theorem. Okay. So hypothesis testing we know, so that part we're jumping. So it's just like a quick recap, right? You have null, you have alternate hypothesis, right? So then you have test statistic and so on. So now comes the question of confidence intervals. This is the other coin. Where you want to come up with, if you're estimating the mean, so you don't know the population mean, so you only know the sample mean, which is this value. And then you're saying the population mean will be around this interval around the sample mean, plus this value is the lower limit, minus this value is the upper limit. So that is what you're doing. How are you doing that? Because now if you know the distribution of your sampling sample statistic, which is a sampling distribution, based on that you can do cutoff points and say, okay, less than this there is 2.5% probability if I took this as a cutoff point. More than this, there is 2.5% probability, which means this and this combined 5% probability, which means inside there is 95% probability, because the sum of probability in distribution is always 100% or 1. So inside you have 95%. So you can say the true mean with 95% probability or confidence is between this value and this value. But then if you wanted 99% probability, then this you have to reduce. You have to move this even further. So that is how when you change your confidence that you're looking for, your upper limit and lower limit is changing accordingly. Okay. If you're okay with 70% probability, then you might come something like this. So but basically we are cutting off the probability away from the tail. This is known as the tail, right? Tail is where you have low probability events as far as Gaussian normal distribution goes. So this is where you can cut off and say more probability area inside. So critical value of z refers to that cutoff point basically. Into so times the standard error. Okay, now let's see the derivation. He wants confidence interval for mean, for example. So he knows the mean has this distribution. So you want to find what these cutoff values are. But for this, so what you can do is you want for mean, right? The central limit theorem says the follows: if you subtract x bar minus the sampling distribution of the mean of the sampling distribution of x bar. So x bar has its own distribution, I said, to keep things clear, not to confuse. And I said it has its own mean, it has its own variance. So for any random variable, if you subtract its mean and divide by its variance, what you get is known as z, which is known as a normal with 0 mean and variance 1. So this is the distribution. So now you want confidence interval around x bar. So you're sending sigma x this side and that side. You're sending this x minus mu in the middle. You can keep mu and you can send x bar that side, because you want for population parameter, not for confidence for population mean, not for sample mean. So you send that, then you get this distribution. Then you get this interval. So that this interval, because only mu is in the middle. So that's how you got confidence interval. In the above page, he wrote, right, lower limit was this, upper limit was this. So that is your confidence. If it falls within these, you can say with probability 1 minus alpha, based on your choice of alpha, you will compute upper limit and lower limit, because this depends on alpha, this depends on alpha, the cutoff points. And you will say mean falls within these two intervals. That is the overall idea, foundations of statistics for confidence intervals. Okay, so that is how we derived this. But as you see, if you want to compute this, you should be knowing sigma. But sigma is rarely known, because you only know it is normal behavior. You don't know population variance, you don't know population mean. You only know sample variance and sample mean. So obviously what is the best you could do is you can use the sample variance. So but we can use best estimate of population variance, sample variance. So here instead of population variance, you're putting sample variance. This is sigma x bar, not sigma mu. Okay, so then what happens is your distribution is no longer z distribution, it is t distribution is where your behavior is coming from. So based on t distribution, you are making the cutoffs. This z alpha by 2, t alpha by 2, this part is always the cutoff part. This sx or sigma x is always based on the sample variance part. So based on this variability, based on the distribution, these are the cutoffs for getting 1 minus alpha probability. That is the idea here. This is the t distribution. This is also known as student's t distribution sometimes. So here, instead of x bar minus mu by sigma, which we used as the trick in here to get the distribution for x bar, but sigma is not known. So what you do here, you put estimate of sample mean, the sample variance, which is s by root n. That is what you do. Then you have this statistic will have t distribution. So let me say why I said this is another kind of hypothesis testing. In hypothesis testing, you had test statistic, you know what distribution the test statistic was. Same thing here. Now you are using that. To use that distribution, you are choosing cutoff points based on confidence interval. I gave you distribution beforehand, and all you have to do is find cutoff points based on whatever alpha you want to choose. And based on that, you get lower limit and upper limit for the mean parameter. And that is what is going on. So instead of looking at this plot, you can also look at the same numbers in part of a table as well. So you know 75% probability where what the number is, where what number is coming with that. So there are different kinds of confidence intervals, obviously. So if the population distribution was normal, like in that cartoon example, and any sample size, could be large sample or small sample, and if your population variance is known, then this is your confidence interval. Because this is based on normal distribution cutoff. 1.96 is the 95% probability cutoff for normal distribution. So the z alpha by 2 ended up this much in the table or in that plot when alpha was 0.5, which means 1 minus alpha is 95% confidence. But if population variance is also unknown in your situation, which is very popular, then you use the estimate of population variance. So then you have a confidence interval based on t statistic, because then the distribution is t distribution. If your population distribution is not normal, because school or heights of students may or may not be normal, some other thing you're measuring may or may not be normal distribution behavior. And if your sample size was large and if population is known, then again same thing. Unknown, then this thing. So and so. If it was binomial, which means like the toss of coins, right? Binomial distribution means it's a discrete distribution. You're trying to compute what is the probability of success of an event. So like what is the probability of tail occurring or head occurring? Could be success. Other thing could be failure, like 1 and 0. So if you're having 0, 1, like on-off events, that is what you're measuring in your data. Then all you can look at is proportions, right? Which is the so if your proportion of ones is 0.5, proportion of zeros is 0.5, then probability is 0.5. But if proportion of ones was high, which means maybe tails is more probable, something like that, right? You want to make confidence interval based statements around those proportions, where p is your proportion, probability of success is p. Then this is the confidence interval for that. So this is the cutoff point. This is the variance actually. Because if you see, if I search standard deviation of binomial, you will get this value, this formula. P times, this is known as Q1 minus PQ by N is what you will get on VK as well. That is the idea. So basically around your statement, you're coming up with some error bar before and after. That is what is the confidence interval idea is. Now say if you're computing difference in means, this is interesting. So you have two columns of data. You want to see if the means are significantly, what is the confidence interval around the difference, right? So it gets tricky. It's easier if the variances in the two columns are similar. But if there are different variances, then what you do in computing your S or your sigma or this, this is the table. This, you always have the cutoff and then you are multiplying with some term of variance or deviation, right? This is all the variance or deviation related terms. In that term, you cannot just use one variance because you have two variances, be it population variance or sample variance, because two groups have two different variances. So then people use what is known as pooled variance. You are just doing this. You're summing up the variances. And then you're using pooled variance. So this thing is the same as this formula if you do the algebra. So depending on that situation, you get again different confidence intervals. So here you see confidence interval for difference in means. Before was confidence intervals for means, right? Just for average. Now you are saying confidence interval difference in means across two different groups, two different variables. Again, different situations. Normal distribution, sample size. If population variance is known, then you get this thing. You are using sigma, which is the true population variance. But you are doing pooling because two different variances for each column. If population variance is unknown, then you're using sample variance in that part. So there, instead of using z alpha, you're doing t alpha now, because it is no longer z distribution, it is t distribution. Similarly, if this is if variances are unknown but they're equal. If they're unknown variances and they're not equal, then you're using this formula. How were each of these derived? They were derived historically quite a while ago using the same concept here. You use central limit theorem to say that this quantity is always z distribution. So then you know the cutoff points, because if you know the distribution in that image I showed you, right, you can have cutoff points based on your choice of alpha. And so then you are just rearranging this quantity. You want distribution around mean, so you send everything else this side and that side. So sigma x goes this side, sigma x goes this side. And x, then you do subtraction so that this becomes positive, this becomes negative, and x also goes that side and this. So same thing, x bar went off that side, x bar went off this side. So mu is left out. So this is your interval. If you know the distribution of the quantity in the middle, basically, then you can always choose cutoffs and say, play this game of what parameter is required, you keep it in the middle, everything else is sent this side and that side. That's how the math works. And then you get your formula for the interval. This is the exact formula he wrote in the table. Okay. And when he wrote 1.96, because he chose alpha equal to 0.5 in that table, so for z alpha by 2 is like z 0.5 by 2 in table will be like 1.96. That is exactly how he derived each of these. Depending on what the distribution of the middle part term is, you are getting different things coming up here. Same here. This is cutoff term. This is variance term. You just rearrange terms. That is how these things are derived. Now again, instead of difference of mean, you can say difference of proportions. So say click-through rate. Say what is the difference of proportion of click-through rate across Amazon website homepage versus eBay web homepage, right? You know, maybe Amazon is more popular, but sometimes maybe something you're measuring, you don't know, maybe a Samsung ad versus Galaxy ad versus Apple ad on CNN's website. What is the difference of proportions? So just difference of proportions has a lot of variability in itself. It has its own distribution. So you want to account for that variability and come up with confidence interval for the difference of proportions of what is the proportion of ads that were clicked. If you showed million ads for Samsung Galaxy and million ads for Apple iPhone, which one was clicked, then you will know what is the difference. You know, sometimes you might think they are similar, sometimes you might think they're different. So now that is why here now we saw confidence for mean, we saw confidence for difference of mean. Now we are looking at confidence for difference of proportions. So this is the same concept. Here you are getting pooled variance. Now you see that's why two variances he added up. Pq by n is one variance, Pq by n is another variance. This P1 means one group variance, P2 is group variance for another one. 1.696 is the cutoff value based on 95%, means alpha 0.5. Then you got the difference of means. So I can again find distribution. I can go back in reverse of my derivation as well and say, I can send these terms here and there and say, oh, this is the distribution of the central quantity. Also another way. Recap. We basically covered confidence intervals actually. So now you can see what he did here. This is the constant for normal in this slide. This is for T distribution, for chi-square distribution, so and so. Anyway, so that is what I wanted to cover. Any questions or so? We covered Anova and confidence intervals. Non-parametric test, I'll just say one or two lines about it. If you saw confidence intervals and hypothesis tests, we were always going with some distribution assumption. We were saying, what if the data is binomial distribution? What if data is a normal distribution? But say if you don't know what the distribution is, and if it does not satisfy any of these classic distributions, it is having its own distribution. It is neither normal nor binomial. Then how do you even generate? Because if the distribution fails, your test statistic or hypothesis testing fails, your confidence intervals also doesn't hold good. The distribution itself is not satisfied. So then comes the area of non-parametric statistics, which means regardless of distribution, you can do this hypothesis test. So for example, instead of t-test of comparing two means or z-test in comparing two means of two variables, you can do Wilcox and rank sum test. Similarly, instead of Anova, you can do Wilcox and rank sum or Mann-Whitney test, but in terms of Anova, you can do what is known as Kruskal-Wallis test. So Wilcox and rank sum test. There are many non-parametric tests, so I just wanted to say these are available in R and SPSS and Python everywhere as well. So if you read this, Kruskal-Wallis test is again Anova, but is based on ranks or odd tests, but is non-parametric test. So it can be used to determine if there are statistical significant difference between two or more groups. It's exactly Anova, but it doesn't require any distribution assumptions. Like F test was the assumption in Anova, right? Ratio variance and all that. Here it is, regardless of distributions, the test will work. So you will again have p-value. That is the idea of Kruskal-Wallis test. And Mann-Whitney test is a version of, unlike t-test, exactly, this is what I'm saying. Unlike t-test, it does not require assumption of normal distributions. It is nearly as efficient as t-test or normal distributions. So even if your data is not normal, then you can use Wilcox and non-parametric test. These are more later developments. These are like famous statisticians and stuff over the last few decades. So there are many non-parametric tests. That's what I wanted to refer to. It's a separate course in itself of how the non-parametric test works, but still If you're solving the same problem, you still have some p-value, you make decision. Okay, so we covered this part, we covered these two, we have MDS. We covered PCA last time, we have MDS. Multi-dimensional scaling. Okay, this is very useful for visualization in general. So basically, I give you a bunch of data records, and then you can compute the similarity or dissimilarity or distance between the records, right? You can say these records are similar or different by computing some distance, for example, Euclidean. So if I give you this distance matrix, how do I plot the data in 2D or 3D, 5D, whatever dimension? So I give you this distance matrix, this is the left hand side. I want to plot it. So say this was, so we want to go to the plot so that if you look at any 2 points, EGY, Brazil, whatever distance, that distance in this plot should be same as the distance we originally computed in here against EGA versus EGY and BR. So that is the idea here. So how do we, that is what MDS is trying to do. So an example. So this is distances between colors. This is a weird example actually. How distant is yellow from green or red from black or black from white? They took 14 colors and they found pairs of distances between colors. Right? So like these two colors are similar, right? These two similar. This is very different from something like that. So then they did MDS. Then they plotted each color on the MDS scale. So now you can see, oh, these two colors, what are these two colors represent? Those are similar. This color and this color is a little different, like that. That is the idea of MDS. So the way it works is again based on Eigen decomposition. So it is actually fairly complicated. Actually, the paper I published also uses some MDS related stuff. So the theorem goes by this actually. You compute distance matrix B, which is your original input data, this distance matrix or similarity matrix. Then the theorem goes by this. If you compute distance matrix and then using the Ij means ijth entry of the distance matrix. D dot j square means the mean of the jth column of the distance matrix. This is ith row. This is mean of everything. Okay. And then if you compute this entry and call it Bij, you do this algebra and call it Bij. And then if you compute the B matrix where every entry Ij has this Bij, the beauty is the beauty is then if you compute the Eigen decomposition of that B, so let me tell you, I know I'm going, like I know stuff that I know is not foundational in this part and in this context, that I know that I'm just probably speaking way ahead of stuff. So, oh, why is this not open? Let's see. Anyway, yeah, this is what I wanted to write. Yeah, this part. So what is Eigen decomposition? Last time, this is a very linear algebra topic, right? So it says any square and symmetric matrix can be decomposed into a product of these three matrices, U lambda U transpose or V lambda V transpose. Middle matrix is diagonal matrix. The entries in the diagonals are known as eigenvalues. The columns of this matrix are known as the eigenvectors, right? So the theorem is, if you compute the Eigen decomposition and then you compute V lambda per half or lambda per half times V, then you will get the points that will actually satisfy the distances. It is a theorem actually. So basically, if you have distances, you want the points, right, that you can plot in 2D or 3D. So if you do compute that B matrix from the distances and compute that Eigen decomposition and then you compute U lambda per half, E lambda per half using Eigen. Then you get these points is what the theorem is saying. And the theorem says if you compute distances here, it will be as close as possible to the distances here. As long as this distance matrix is Euclidean distance matrix, and as long as it can be represented in 2D. If it is not exactly same, some approximation is coming, then all you can do is increase the dimension. Try to come up with 3D points. Means you use 3 eigenvectors instead in computing X. Then you get 3D points, then it will be even better. But if your distance was not Euclidean distance, Euclidean means the straight line distance that we studied in, in our +1, +2, in our school, high school and college and stuff. So how do you compute Euclidean distance between 2 points? x1, y1, x2, y2. The formula is y2 minus y1 whole square plus x2 minus x1 whole square, right? Say if this was your axis, right? If this you point here, you have one point here. You want to see how the y-axis is varying between these 2 points and how the x-axis value is varying between these 2 points, right? X-axis means this much versus this much difference. Y-axis means this height versus this small height difference, right? So that's why the formula was y2 minus y1 whole square plus x2 minus. Now if you had x1, y, in 3D you have one point x1, y1, z1, second point x2, y2, z2. And the difference between those 2 points is z2 minus z1 whole square plus y2 minus y1 whole square plus x2 minus x1 whole square. So on. So same thing, you're doing sum of squares of the dimensions you're adding up. So if you have that kind of a distance matrix as your input, then the theorem holds. But if your input was like some survey result, what do you think these 2 colors are different? Then some guy will say, I think they're similar by 90%, 0.9. Some other guy will, the same guy will say, oh, these 2 colors are different, equals half and half, almost, the difference is half and half. And he'll say something. Then it is not Euclidean distance, it's his estimate of what he thinks the similarity is. It's like a survey. Or you're computing some other curved distance, many kinds, or maybe distances between 2 images. So if you have 14 images, some computation you're doing to compute distance between images based on their colors and illumination, lighting, everything. So you can have different kinds of dissimilarity measures. Then the theorem does not hold. Then you will have some approximate result. That is what he's mentioning. Is it Euclidean distance you're dealing with in your input or non-Euclidean distance? If it is Euclidean distance, then it will be as close as possible. Otherwise, it is not necessarily guaranteed. That is the theory of the multidimensional scaling. But this is also again available in your R and everywhere in one shot, one function. You give the distance matrix, it will give you the answer. So say this is an interesting real life example. They computed airline distance. So what is the distance that a flight takes from going to Cape Town to Beijing? Not on the globe, but in the airline, right? Because it might go via Paris. I don't know. It's I mean, it won't go. Both are Africa and Asia, right? So it may go via Delhi. It may go via Vietnam. It's up to them, right? It may go via Singapore. It may go directly. It may go straight curve. It may go round curve. Whatever the safe and prescribed path is for any given airline. Right? So these are airline distances between each thing in miles or whatever. So then you can compute these eigenvectors. You compute the B matrix. You compute eigenvectors and eigenvalues. Here he's doing 3D plot. So he took 3 eigenvectors. Then he computed these points. So now he's showing, oh, airline distance between New Delhi, Singapore is like this. Singapore and Hong Kong is slightly higher. Hong Kong, Beijing very close by. It's obvious both are in same country. Melbourne, Tokyo, Japan and Australia are kind of close. And obviously Tokyo and New York is far off. New Delhi and New York is even far off. But Tokyo and Honolulu is close by because we know on the globe, Japan is somewhat closer to Hawaii than Delhi or Singapore or Rome. That is exactly what. So you're really what you know about your world is what is showing up in this result just doing this theorem. This is one way to say. Now if you had some distance metrics where you don't know what the distances are, all this understanding, here you have understanding of geography, but if there's some between genes, for example, you don't know which genes are similar, which genes are far away. Then you will do this and then you will say, oh, these genes are similar. Then you will say, oh, okay, these genes are similar and they're all cancer causing, or one particular cancer they're causing, for example. Then you're learning more and more about it. Then you know what is the next group of genes similar to that. You can come up with all these analysis. Once you have the plot, you can do analysis, paralysis, whatever you want. So that is the idea here. So that's what he wanted to show in this example. That is the idea of MDS. So here, gene expressions also was an example. This is gene expressions, right? Genes are very genetic values are very complicated. So you are looking at some 250 genes here across these many people, and you're trying to see. But he didn't show the MDS for that because it went off into another topic. But yeah, these are all MDS. So this is an MDS on letters actually. Letter recognition. Interesting. If you see C and letter G, they're similar, right? The curve C is like that, G is like that, but G you are adding this part. So that similarity is showing after you did MDS. So and so M and H and N are M and N. These are kind of similar, but N, H, M, W, these are all straight lines. They are not curves. So that's why N is not very far off from C or from G. They're different curves. So here is look. He did MDS on distances between letters, between the geometry of the letter, the shape of the letters, basically. Any questions? That brings us to the end of this entire syllabus, actually. Like whatever we left out, this thing and this part we covered, actually. Okay, so
I think
sorry.
Pretty good.
It was very choppy. Sorry, I know you said pretty good. The signal was choppy. Can you say again? Sorry. I'm not able to hear properly. I'm just guessing you said the course was pretty good or something.
Yes, and I think the thing is we really need something to practice and put this knowledge into practice.
Very true. As long as you can do assignments, that will give you a lot. Do random forests, apply SVM, apply neural networks, apply on image data, apply on whatever data, housing data, Kaggle data, or UCI machine learning data. Apply MDS, apply PCA. There's so many things you can do. Hypothesis testing, confidence interval.
Yes, definitely.
If machine learning is popular, I would say at least do projects on regression classification, random forest, neural networks, SVM first. That will give you the most impact in the machine.
Definitely, we need more time to process all this.
Right, of course. Your learning will always continue. So one thing I can show is the landscape around. So let me share screen then. This will not take more than 5 minutes or so. 5 to 10. So actually, it's hard to draw the landscape. What I will do is open I will do both as and when required. I'll open Google Doc. Okay, so yeah, I will start now here. I will keep adding there. You can see the screen, right? I guess.
Yes.
Yeah, okay. So you obviously have regression. You have classification. Within regression, the most foundational one is linear regression. Then you have GLM, it's a family of models which has logistic regression, Poisson regression, GLM models. There is GAM, generalized additive models. Then you have all the machine learning type techniques like SVM, random forest, so on, neural networks, etc. Right? So I'm not listing this is another family. And then you also have time series analysis, which we did not cover in this course. Time series based regression. So within time series, you have again different models: ARMA, ARMA. Then this is known as auto-regressive moving average model within time series. So time series means, what is time series versus normal data? Normal data, your row is not indexed by any time instance, timestamp. Time series means like stock market. At this particular time, what time is it now? 9:38. What is the Yahoo stock, Verizon stock, Microsoft stock, Amazon stock. Johnson stock, whatever. That is time series. Every data point you're collecting is also indexed by timestamp. So there is a dependency across time. So what is today's price or current price is dependent on what is price in history. That is not the case in other data sets, non-time series data sets. So you have ARMA model, you have a GARCH model, GARCH. These are different models, come with different assumptions and everything. Okay, these are some different kinds of regression. And then similarly in classification, you again have logistic regression, which is a part of GLM family, which is here. Then you again have, not SVM, here you have support vector regression, SVR, but people interchangeably call it SVM. You have SVM for classification, you have random forests, neural network. There are many techniques. Okay, there are like 10, 20 techniques, neural network, so on so. So this is all supervised learning. Okay. How are you guys, like, are you guys listening, or do you want to take a snapshot? I don't know what you want to do here, because I'm using a lot of abbreviations as well. You might as well forget what these are.
Sure.
It down. I'm thinking how, because landscape is always a big landscape, right? So I'm trying to see how I can get this across to you. Do you think I should type or like what?
I just took a screenshot.
You took screenshot. Okay. I can erase it. Is that okay?
Yeah.
Okay. We did that. So now we looked at supervised learning. Supervised learning, right? But then there is unsupervised. Under this came the previous screenshot. But then you also have unsupervised learning. Because here you only have input variables. You don't have regression column, what column to predict or classify. You don't have labels or responses. So under this, we have clustering. We studied some regression in our course. We studied clustering in our course as well. We have clustering. Clustering. Okay, then there is another learning known as semi-supervised learning, somewhere in the middle. Semi-supervised learning. Here, okay, you know what? At this point, I have to type. That is better. Supervised learning, unsupervised. Then you have semi-supervised learning. Within semi-supervised learning, what is semi-supervised learning is the question, right? Here you have labels or response. Both are available. Here only features are there. You don't have labeled or response variable. You don't know which email is spam, which email is not spam to train your data. Supervised learning, features obviously are there, input variables. And then you have
Some label.
Labeled, yeah, plus unlabeled. Right, so some labeled, some unlabeled. Some rows are labeled, some rows are not unlabeled, not labeled. Okay, this is semi-supervised learning, and in this you have just like I mentioned techniques on these two. So within clustering, I also came in spectral clustering, everything comes up. So in semi-supervised, you have label propagation. You have the different techniques. Okay. Then you have transfer learning, where you have source task.
Pranit, this is really good. Can you add the previous slide also in the same text?
Yeah, I can definitely do that. So supervised learning, yeah, definitely. So you have, I think the text is better because it is big. That's why I thought it's onto.
Then we can upload into your Google Drive or publish this to us.
Exactly, I agree. Regression classification. In this you have linear regression, GLM family of models, and generalized additive models. We can also have actually GLMM. It's generalized linear mixed models. You have GAMM. Okay, so many techniques within this each family itself. And then you have SVR, random forest, NN, deep learning, regression trees, CART. We have BART, which is Bayesian additive regression trees, node harvest, different tree-based techniques. So many techniques are there actually. So many techniques. Techniques, there is no shortage. Same thing, same thing. Okay, now unsupervised learning, we have, there is also time series regression. Autoregressive moving average model, GARSH. Some people call integrated moving average, so it depends what have you. Okay, then there is classification, unsupervised learning, you know. It means clustering. You have manifold learning, MDS, right? Multi-domain scaling, PCA, so on so. Okay. In manifold learning, you have isomap, Eigen maps, PSA, fusion maps, Semi-supervised learning, you have features, then you have some rows are labeled, some rows you don't have labeled. So some emails you know they are spam, some you don't know they are spam or not. So, well, some emails you know whether they are spam or not, some emails you don't know whether they are spam or not. So there are some techniques there. Transfer learning, you have two different tasks. You can call it source task, domain task, for example.
So Pranit, there is one I heard like in my previous project they used.
Sure.
Short-term memory.
Yeah, LSTM, long short-term memory. LSTM.
Where is that false is supervised, right?
It is supervised. It falls, but for sequential data. So it falls here. Supervised, but it falls in here. Time series regression. Right? So the difference is here you're predicting numbers like stock prices. That's a good point. You can call sequential. So I wanted to put this separately. Sequential data analysis. So I will put it. It will come under. So basically, say if I'm typing on the keyboard in Google, where is Google here? I'm typing Praneeth. Then it is giving suggestions, right? So many Reddy, so many Praneeths. How are these suggestions? How is it predicting the next state? If I'm typing, Martin, it automatically gives suggestions. Martin Luther King, I have a dream speech. Martin Luther King, so many things, books, speeches. How is it coming? How is Google predicting beforehand what you want to do? What is the next state? So you predicted, you do 2 states, what is the next state it should be? So that is known as sequential data. So here you're not predicting numbers, you're predicting states. So similarly, state would be like this as well. So state space. Yeah, all these are state space models. I'm saying one thing is more nicer than the other. Anything is okay. So that's good. So here you have different states A, B, D, C, K. This could be different names, different words. This could be, like say this guy is running state. Then say some action happened. He fell down. So this is fell down state. If he fell down, next state is he's injured. If he's not injured, he's again going back to walking, I guess, because he doesn't want to run anymore. He wants to walk. He walked for a while. He's happy. Then he's again going back to running, but he again fell down. So here you have what? Walking, running, fell down, injured, not injured. These are all different states. So from one state to another state, you can only go when you take an action or if there is a possibility. Sometimes there will be states that are not connected. So B to C, you cannot go directly. Only way you can go to B to injured or B to hospital is if you run and fall down, then you go to C. This is known as a state space diagram where connections tell you what actions, and then there's always probability. Going from one state to one state might have more probability, one state to another may not have more probability. So all the speech processing models, speech recognition, speech processing models, they are known as sequential models because after one word, which word is more popular? So these are all hidden Markov models. So these are sequential models. So LSTM falls here. STM is for sequential data, sequence prediction. So one state to another. So LSTM could be used for that, but also a special case could be for time series. I can put here, but then I have to also do this thing. Sequential data analysis, but that will come later. I will do later in the bottom. So yeah, transfer learning. So this falls under deep learning actually. So within deep learning, I can always expand again if you wish. So you have here also I can act deep learning. So in unsupervised, you are doing what you can do is auto encoders. This is a deep learning technique architecture. In supervised, you have here in time series you have DL, LSTM. Here you have forward. All neural networks, different kinds of neural networks. LSTM means long short-term memory. Okay, so where are we? Here, transfer learning. So here you have two tasks or problems: source problem, domain problem. So you want to transfer your model for source problem. So you build one model to do one classification. You want to use that intelligence to do classification of completely different tasks, but you want to use this intelligence as well. So this is known as transfer learning. Similarly, there is domain adaptation. So I want to do one table Yeah, this table. I always bookmark this. Like this table. This table. It's too big there. Is better. So there is something called domain adaptation, but everyone gets confused. So transfer learning, many kinds are possible. Okay. If you have two domains, two tasks, right? Source task, target task, target domain. Obviously, you can do transfer learning with regression or classification either way. So if you have source task, your labels are available, and target task also labels are available. Then you will fall in multitask learning. Source task, you do not have labels available, like an unsupervised setting. But in target task, you have labels available. Then you have self-taught learning. Then another paradigm, domain adaptation. Source task labels are available, but target task labels are unavailable. It's like other way around. Then it is domain, it's other way around of self-taught learning. Then you have domain adaptation or sample covariate shift models. So these are known as inductive transfer learning. They're known as transductive transfer learning. So that is the bigger point. That's why I said I want to use this. And what I will do is for the benefit of us, since we are doing transfer learning, there in our landscape, I will put this. Put it in there. Okay. So that is my favorite slide for transfer learning. Oops.
You can put that slide there. You can cut it.
Yes, that is my idea. I just did that actually. I could have cut it better. There is something cut, but yeah, information is there.
Yes,
because as you imagine, these things can happen. You can
use snip table.
Tables can be available and unavailable in different formats. Okay, then transfer learning is done. And there is active learning. There are a lot of things, even I'm surprised a lot of people don't know about active learning. Okay, even in Amazon, there are a lot of research scientists that do not know that this thing exists, but it is still very applicable and useful. There are a lot of people who do know about it as well. That's what I meant. I'm not saying it is one thing that no one knows. Okay, active learning is even an interesting setting. Features are always there, of course. Input variables should always be there. Okay, labels only obtainable on a query by query basis from Oracle. Oracle is like God. It's like wise guy. That's not who wise person, but he charges you. Okay, so the setting is like this. You have features, all are there. Initially, you don't have labels at all. Well, plus some labels, plus any other label only obtainable on a query by query basis. In some special case, some labels will not be there. You'll only have features and none is labeled, but any label you can obtain on a query by query basis. So the thing is, Oracle is like wise guy, like God, right? But he charges you. Means what? It is not easy to get labels. In general also it is not easy to get labels, but here especially it is not easy to get labeled data, which means you either have to do crowdsourcing, for example, right? Like Mechanical Turk on Amazon. Or, say it is fraud detection setting, right? Say you are having a team of investigators all across the world, Shanghai, Hong Kong, Bangalore, Delhi, Hyderabad, New York, Seattle, South Africa, right? So you are paying them millions of dollars in terms of running these teams, so many salaries, so much cost. But then you only want to use their specialization in investigating accounts of whether they are fraudulent behavior or not very carefully. You don't want to send stupid things which you already know are fraud or not fraud. Because if you send them too much, you're using too much workload, which means you have to hire even more investigators, right? So you can only label in a smart way. You don't want to use their valuable time and money in a dumb way, where you say, where you say, Amazon has maybe a billion or million accounts. I will send all million accounts every day to to investigators all over the world. It's very stupid, right? It's impossible. You're going to spend more than the amount you're getting in just investigating and paying their salaries. So what you want to do is you want to select smartly only those records you think are the harder problems. Like these are the ones that are really hard. These are the ones that the investigator will look at hands-on. He will do his investigations, or he'll talk to FBI, whatever, police, whatever is required. But you won't investigate everything else. So you want to smartly use the knowledge of the oracle on a query by query basis. So you want to query only those records and send only those features corresponding to those records, those rows for which you want to get some label definitely, so that your model will improve. So here there are again different ways to do it. So by example. Okay. And there is cost sensitive. This is getting very popular these days. Cost sensitive machine learning. So there is cost associated with different features. Or records. So you want to be careful in using what variables. Some variables may be very costly to collect. Maybe it's some mechanical engineering, some I don't know, whatever it is, reason. Some variables may be easier to collect. So you want to, there's a cost associated with it. So you only want to, you want good classification, good regression, prediction performance, but you also want to keep cost in check, or you want to be sensitive about it. So this is cost sensitive machine learning. Yeah, this covers a lot actually. But then there is a separate set of things people will need to know, which is things like the hypothesis testing, constant interval, that kind of stuff. There is hypothesis testing. There is multiple hypothesis testing, also known as multiple comparisons. Confidence interval. Prediction interval. Prediction interval means confidence interval around your prediction basically. So your regression function, you have some regression plot you predicted around that confidence interval.
And distributions.
Yeah, all that. Yeah. That is generally in statistics, right? You'll have distributions. So that is more like foundations of statistics. So it's like cumulative distribution function, PDF, probability density function, quantiles, which is inverse CDF. Then you have Bayes theorem, conditional probability. Then there is again within Bayesian statistics, you again have Bayes theorem, CMC. These are more complicated stuff. Markov chain, Monte Carlo, example. Yeah, I mean, these things is like, if you open any good book or a few books, you will see so many topics. I don't want to write contents of books here in general, so that I'm not writing too much about this. Yeah, I mean, there is so many things I can talk about. Sufficient, like it will become like a very more and more I put in, it will become more complicated course. But anyway, that is the thing. But here the modeling landscape. Then yeah, one thing Venkat brought up actually. Sequential data, right? That is one that will come here actually. Data analysis, reinforcement learning, state space models. These are different things meaning similar stuff, slightly different stuff there. In reinforcement learning, state space model means there are a bunch of states and actions, state, action, state. can take. Based on action, you go into another state. There is state and action space. But then also in reinforcement learning is a special case. You go from one state, you take an action, you go to another state, but you also get a reward or you get an award. Like you're going into worse state than where you are, or a better state than where you are. These kind of things. That is reinforcement learning, and based on that you want to learn. So this is more like human learning actually. So this is how a baby learns, right? Say to walk, the baby is trying to walk, he or she will fall down this side, that side, or one leg goes this side. All crooked things happen while they're learning to walk. So she's getting awards and rewards. When she's doing good things, she's getting an award in her mind. She's liking that she's walking. She's getting good feedback. When she's falling down, or if she's falling down, they're getting either pain or getting disappointed. They're getting afraid. It's a negative feedback. So the nature is giving us positive and negative feedbacks, so that we reinforce our learning. What thing we have to do, what thing we should not do. That's how a baby, when they're too young, they don't know that if they fall down from the stairs, they're going to break their head. But once they're more than a few months old, they very clearly know that they should not fall down from the stairs. At least attempt not to fall down. That is how, through reinforcement, they're learning positive and negative actions. That is the idea of reinforcement learning. So you have states based on actions, you get rewards, or awards or punishments, and you go to another state. So this is reinforcement learning. Similarly, imitation learning. Through imitation, you're learning. There are models for these as well. So very popular actually. Reinforcement learning is becoming very big these days. So learning, there is what is very popular is Q learning. Then there is deep reinforcement learning. There's PD. Temporal difference model. Okay, then within state space, action space, in general, what is very classical is known as hidden Markov model, Viterbi algorithm. This is very popular in speech processing. Most advanced speech processing systems that do speech recognition still use hidden Markov models, right? So especially when you call your call center company and then it tells you, can you read your credit card number or last 4 digits or social security, and when you read it, they recognize it. It is being done through a hidden Markov model. So it's an intelligent thing, it's a learning model, for example. Okay, so we have all these things. Series models, LSTM, deep learning. The long short-term memory. Okay, so many things like this. I mean, yeah, I can keep going, I guess. Something and this and that I can keep adding, but I think this is a good start.
That is pretty good, and even this also takes at least a multi-year project.
Yes, exactly. There's so many things going on here. Yes.
I know. I think, after your class, I decided to join to MS Statistics.
But really?
I'm sure, really.
But one thing you have to be careful though. Some courses are very calculator driven. You are only hitting calculator like you're doing some accounting course. Although there is nice subject involved, the universities sometimes make it feel very mechanical.
Mm-hmm.
Some courses are very theoretical. You learn very high-end math. It can be very hard in that sense. These are the negative parts based on you like it or don't. Then there are some that are more about these models and stuff, which may be more practical. But if someone is going through all these different theory, calculation, practice, everything, of course he's becoming better and better a statistician or person. But yeah, but something one has to keep in mind though.
I want like a like an analytical based only, like a modeling perspective.
Right.
Maybe after 5-10 years, then I want to start my tuition classes here for kids instead of going.
Yeah, absolutely. I think if there is demand for grown-ups for data science, there will be demand for kids as well for statistics.
That's our plan. After 5 to 10 years, I want to start my own school here. Simple, like how we'll run a SAT score school.
Right. Yes.
TOEFL, GRE. Similarly, next is a statistics school.
Right. Possible. Yeah. Since the world is changing, then it will be even more demand for kids as well, I guess. Maybe.
Yeah. Cool.
Just like C programming or whatever. Yeah.
And this is really good now.
Yeah. So I have to share this though, otherwise we will lose this.
Yeah. V Minupala. Yep.
It's Chun Wang, right?
Yeah, the first one.
Yeah. So, but I can send to others also. Why am I doing very slowly? So see there. No, why 2 he sent? Both are same guy. That's the only system. This is all right?
Okay, yeah, that.
Okay. Oh, Hemant.
Good. You can copy yours also.
Mine I will have in mine already. This is mine. Yeah.
Okay, got it. Let me see.
Okay, cool. So yeah, this is something. All right, then. So yeah, looks like we made it through a lot of lessons and courses and sitting in weekends. So I'm glad you guys sat patiently.
Very good, Pranit. Thank you very much, and pretty good. You covered really good information. What exactly I'm looking, that's what covered.
Sure, perfect. So yeah, so keep in touch and please do assignments, especially the ones for searching for careers. Okay, so that is the most important. All right, then have a good one.
Definitely.
Yes,
Thank
definitely.
you, Vanessa.
Appreciate it. Thank you. Bye bye.
Thank you. Bye bye.
Yeah.